characterization of lock-in amplifiers. So let us first see what is a lock-in amplifier. Lock-in amplifier is a precision instrument used to measure the amplitude and phase of extremely small AC signals even when they are buried in noise. As we can see in the image below, we have a block of lock-in amplifier where the input is a signal from a device under test and other signal is a reference signal. So we see the block diagram of a lock-in amplifier. At input we have a signal which is from the device under test. So the next stage comes with the mixer. So we have two signals here, VR of t and VS of t. VR of t is the reference signal. At one side of the mixer we have a signal, and the other part of the mixer will get a phase shifted signal, and then of the output of the mixer goes through the low pass filter, and from the output of the low pass filter the amplitudes of the signal will be squared and added, and then we'll take a square root of them. Let us see the working of the lock-in amplifier. The first stage is signal mixing. As we know, signal mixing, the if both the frequency of if both the frequencies are same, then we'll get a frequency at DC and one at the 2F. The next stage is a low pass filter. The low pass filter removes unwanted frequencies, and we know that we want only the DC signal and we don't want the 2F signal. So we'll make our cutoff frequency such that we get only the DC component and remove the 2F component. In the final stage, we have two signals. One is in phase component and the other is quadrature phase component. As given in the formula below, R is equal to root of x square plus y square. We'll add them with this, where x and y is the amplitude of the signal from the low pass filter, and finally we'll get the desired signal at the output.
The lock-in amplifier of our project has been implemented using this following circuit. The circuit can be divided into three parts. As we can see, the input voltage is fed to a network of these four switches. These four switches of CD4066 IC acts as a switch-based mixer. The output of the switch-based mixer is then fed into an amplifier. The gain of the amplifier is varied, and we can get the amplification accordingly. Then the output of the amplifier is fed to a low pass filter. The low pass filter eliminates all the higher frequency noises and only gives the signal at about 0 Hz. At right, we have the circuit under test. What we are using is a potential divider circuit. We are providing the reference signal, and then adjusting the value of these two resistors, we get a potential at Vin. If we keep R7 low and R2 high, we'll get a very highly attenuated signal at this node. We can use this signal to feed to the lock-in amplifier to accurately get the value of the voltage. Over here we have the comparator circuits. The comparator circuits are required to generate the clock frequency for these switches. The clock frequency is generated according to the frequency of the reference signal. So the reference signal is provided and the comparator circuit generates a square wave according to that. And over here we have a phase shifter. So the phase shifter is required for accurate reading from the lock-in amplifier. What we to get accurate reading, we uh, I, to get accurate reading, we phase shift the reference signal by 90 degrees and then get the output. From the output, we do some calculation to get the accurate result.
We have already seen that we require mixers in a lock-in amplifier, and in our project we have implemented mixer using switches. So we have the circuit diagram on the left hand side where we have switches S1, S2, S3 and S4, and the circuit is designed in such a way that it will work as a mixer. So every switch will require some clocking, and the clocking is given on the right hand side. During phase phi, we will keep S2 and S3 closed while S1 and S4 open. During phi dash, we will keep S1 and S4 closed and S2 and S3 open. This will give us certain circuits, which we will see. So now we will move to the circuit analysis. So when phase is phi, I've already told, like, certain switches will be closed and certain switches will be open. And this will give rise to this equivalent circuit. As we know, V naught equals to 1 plus Rf by Rn into V plus in a non-inverting amplifier. So V naught will become 2 times V in by 2, which will give us ultimately V naught equals to V in, means gain is equals to 1. Similarly, during phase phi dash, certain switches will be closed and certain switches will be open, which will ultimately give us V naught equals to minus V in. Here the gain is minus 1. Now we will look at the waveforms. On the right hand side, we have drawn phi and phi dash. They are opposite of each other, and we are giving V in as a sinusoidal. So ultimately, V naught will become like a rectified signal, which will have some DC value. When we pass it through a low pass filter, we will get the DC component. The DC component of V out comes out to be 2a by pi cos phi. We have the cos phi component, which create challenges for us. So we need to create, again, generate 2a by pi sin phi. To do that, we have to phase shift the input signal. For that, we will require a phase shifter. So here we have the phase shifter circuit. So in our project, we have implemented a controllable phase shifter. By changing the value of R variable, we can change its phase. Here the phase also depends on the frequency and the capacitance. The capacitance is fixed, frequency we can change, and depending on the frequency, we will change the R variable so we get the required phase shift. In our project, we required a 90-degree phase shift, which we have achieved using the same circuit. Now we will move to another very important component of a lock-in amplifier, which is a low-pass filter. We have implemented our project using both passive low-pass filter as well as active low-pass filter. So in this filter, by changing the value of RA and CA, we can adjust the cutoff frequency. We have tried to keep the cutoff frequency as minimum as possible in our project so that we only get the DC component and get rid of all the high frequency components. Here RF and R1 we have kept equal. That's why we will get a gain of 2.
So over here we are having our lock-in amplifier setup, and here, this is the DC power supply that we are using. We are using oscilloscope to analyze the output signals, and this is the function generator which we are using to generate VREF and input signals. So to generate the V input, we are using the function generator one channel, and this is our DUT, which consists of two resistors connected in voltage divider fashion, and the output of that voltage divider is used as a VIN. And here, as you can see, the signal is quite noisy, and we are unable to get the proper peak to peak voltage due to noise. Close. In order to chop the input signal, we are having switches. The switch we are using in this case is CD4066. As you can see over here, we are using the same switch. To operate the switch, we require square wave. In order to generate the square wave, we are using the sine wave from the function generator, and we are feeding it into the comparator. So the comparator gives us the square wave output as shown over here. The output of the switch is connected to the op-amp, that is connected in negative feedback configuration, as you can see over here. Here we are having a potentiometer in order to adjust the gain of the op-amp, and this entire circuit works as a mixer, and the output of this mixer part is shown over here. As you can see, it looks like a full bridge rectified circuit, and this signal is next fed into the filter. We were previously using RC low pass filter, and now we are using active low pass filter using op-amp. The output of active low pass filter can be shown over the oscilloscope like this. So here you can see we are able to getting a DC voltage, and the DC using this DC voltage we can measure the magnitude of the signal that is of our interest in the input.
Now let's look at the characterization of the lock-in amplifier that we built. One of the important characterization parameters is the sensitivity and the linearity. And then we looked at what output. For sensitivity and linearity calculation, what we did was we sweep the input voltage from 100 millivolt peak to 5 millivolt peak, and then we looked at what the output of the lock-in amplifier was. The output of the lock-in amplifier gave in terms of X component and Y component, which is calculated, and the resultant voltage is found. The calculations used is shown in the next slide. So we get output voltage in terms of A cos theta. To find the value of A, we also need a component of A sin theta. We achieve that by phase shifting the reference signal by 90 degrees. After getting both X and Y components, we can find B calculated via this formula. From V calculated, referencing one of the formulas shown before, DC component of V out is 2A by phi into some phase. So using this formula, we can find the value of V result, which is actually V calculated to pi by 2. So these calculations are used in this table. We have the X components and Y components at different input voltages. We have the calculated voltage, and then we have the result voltage. These results are plotted in this graph over here, and the line that is being shown here is as the equation of y equals to x. The points are arranged in a linear fashion according to the graph. We can also comment on the sensitivity using this table. As we can see, at low input voltages of 5 volts, the result voltage deviates from the theoretical value, from which we can get insights about sensitivity as well. Over here we have the frequency response table. We wanted to check when we increase the input signal frequency, what will be the change in its output. So over here we have a low amplitude 1 kHz input signal. The reference signal is also 1 kHz. From that we get an output in X and Y components over here. Using this calculation, we can get its magnitude and phase. So we have done that for a number of frequencies, and we have plotted the frequency response over here. Using this graph, we can get an estimation of the bandwidth and parameters such as roll-off and 3 dB frequency. Over here we have the observations of the frequency response. So the flat response of 34 to 35 millivolt ranges from 1 to 5 kilohertz. The roll-off begins after 5 kilohertz. At 20 kilohertz, the magnitude is about 29.53 millivolt. At 50 kilohertz, the magnitude becomes almost zero. The 3 dB bandwidth is about 20 kilohertz, and the 3 dB point occurs around 18 to 22 kilohertz. So right now we'll show one of the readings that we took for frequency response. As you can see that the reference signal is kept at 5 kilohertz. As you can see, and the input signal is also kept at 5 kilohertz. We then look at the output of the LIA. The output of the LIA can be gathered from the mean, and over here we are only getting the X component. To get the Y component, we need to phase shift the reference signal by 90 degrees. When we do that, we see a change in the mean. The new mean is the Y component and is recorded in the table. So the values that we saw at 5 kilohertz, the X component and the Y component are recorded over here. And from this calculation, we get the magnitude and the phase that is plotted in the graph.
So in order to measure SNR in our lock-in amplifier, first we ground the input and find the output RMS voltage. So in this case we are getting 2.2 millivolt RMS, and now we use the SNR formula that is given here in order to measure the SNR for various input peak-to-peak voltages. In this case we are taking input peak-to-peak voltage starting from 20 millivolt that goes up to 1000 millivolt. For this we are getting VRMS noise, that is also VRMS with noise, that is also given in column 2, and by using this formula we can calculate SNR that is given in column 3. Now we convert that into decibels, so that is given in column 4. We can also plot SNR versus V in peak to peak, that is given in the plot that is shown in the left side. To summarize, a lock-in amplifier isolates single frequency, the frequency of interest, using mixing and low-pass filtering combination. The outputs X and Y allow the calculation of magnitude and phase phi. From the experiments, we have derived the value of the parameters. We are getting linear range from 30 to 100 millivolt. The sensitivity lies in somewhere between 5 to 10 millivolt. The bandwidth we are getting is up to 20 kilohertz, and we are getting stable phase detection across the operating band. Overall, the locking amplifier works as expected, and we are getting the correct values as per the theory.